Terra incognita. When neural networks started doing something we didn't expect. Imagine you build an artificial intelligence system and teach it a very simple problem. You give it two numbers. You ask it to add them. That's it. Nothing remotely impressive. But then you come back after a few weeks and discover that the AI hasn't just memorized the answers. It has somehow discovered the mathematical rule behind them. Researchers gave this strange phenomenon a name: grokking. And it forced scientists to confront an uncomfortable possibility. Maybe we don't understand how neural networks learn nearly as well as we thought we did. 1. The rule that was supposed to work. For decades, machine learning had a fairly intuitive idea about complexity. Imagine you're teaching an AI to recognize chairs. Your training images contain wooden chairs and metal chairs. But when you test it, you show it a plastic chair. A good model should recognize that's a chair because it has the characteristics of a chair. A model that has overfit might instead think chairs are made of wood or metal. It learned the training examples too specifically. This gives us two classic problems. Underfitting. The model is too simple to understand the important patterns. And overfitting. The model becomes so focused on the training data that it starts memorizing details that don't actually matter. So traditionally, machine learning researchers looked for a sweet spot. Not too simple. Not too complex. A kind of Goldilocks zone. This is the famous bias variance trade-off. As a model becomes more complex, its training error usually decreases. But eventually we expect its test error to start increasing. Because the model has started memorizing. And this idea made intuitive sense. Until deep neural networks arrived. 2. Then deep learning broke the rule. Modern neural networks can contain millions, billions, or even hundreds of billions of parameters. That's an enormous number of adjustable values. And here's the strange part. According to traditional machine learning intuition, these enormous models should be spectacularly good at overfitting. They have enough capacity to memorize the training data. So surely they should fail on new data. But they don't. In many cases, they generalize incredibly well. Researchers started increasing the size of neural networks. And something unexpected happened. The training error went down. And kept going down. But instead of the test error rising dramatically, the test error could keep falling. The larger model was actually getting better. This was deeply uncomfortable for traditional learning theory. Because the old story was essentially more complexity, more memorization, worse generalization. But deep neural networks were saying, not necessarily. 3. What if we add noise? Researchers then tried something even more extreme. They deliberately corrupted the training data. Imagine a dataset containing handwritten numbers. An image clearly shows the number 5. But researchers randomly change its label to 4. Now the training dataset contains deliberate mistakes. A sufficiently powerful neural network can memorize those mistakes. And if it reaches 0 training error, it has effectively learned. This particular picture of a 5 is actually a 4. That sounds like the perfect recipe for terrible generalization. Yet researchers found something astonishing. Even when some labels were deliberately randomized, sufficiently large neural networks could still perform surprisingly well on unseen data. This was not supposed to happen. The model could essentially memorize the training data and still generalize. Researchers began calling this phenomenon benign overfitting. Overfitting that somehow wasn't entirely harmful. And suddenly the old picture of machine learning began to look incomplete. 4. Welcome to Terra Incognita. This is where things get really interesting. Mikhail Belkin described this unexplored territory as Terra Incognita, an unknown land, because researchers were discovering that some of the most successful machine learning systems behaved in ways that existing theories couldn't properly explain. Think about how strange that is. We have machines that work extraordinarily well, but our theories about why they work are struggling to keep up. It's almost like building an airplane that flies perfectly, while our equations for aerodynamics are still incomplete. And this wasn't just one isolated observation. Researchers were seeing strange behavior in neural networks, kernel methods, and other machine learning systems. The phenomenon was becoming harder to ignore. 5. Parameters, hyperparameters, and the loss landscape. To understand why this is difficult, we need to look inside a neural network. A neural network contains parameters. In a neural network, these are primarily the weights connecting neurons. During training, the network changes these weights. But there are also hyperparameters. These are choices made by the engineer before training begins. How many layers? How many neurons? What learning rate? Which optimization method? What activation function? How much data? Should regularization be used? These choices can drastically change how the network learns. And then there is the loss function. The loss function tells the network how wrong it is. Training is essentially the process of trying to reduce that loss. Imagine standing on a gigantic landscape. High places represent high loss. Valleys represent low loss. Gradient descent tries to move downhill. The problem? For a tiny model, we might be able to imagine this landscape. For a modern neural network with millions or billions of parameters, the landscape exists in an unimaginably high-dimensional space. And it's not a simple bowl. It can contain enormous numbers of valleys, ridges, and complicated structures. Researchers still don't completely understand this landscape. And that matters, because this is the landscape through which these systems learn. 6. And then something called grokking appeared. Now we return to that bizarre addition experiment. Researchers at OpenAI were training a small transformer. The task was simple. Add two numbers using modulo, 97 arithmetic. For example, 40 plus 59 is equal to 99. But because we're working modulo 97, 99 becomes 2. So, 40 plus 59 is equal to 2. The researchers divided the examples into training and test data. Then they trained the neural network. At first, the network made mistakes. Eventually, the training error dropped to almost 0. At this point, nothing seemed unusual. The network had learned the training examples. Perhaps it had simply memorized them. So the researchers stopped. Or at least they normally would have. But then something happened. One researcher went on vacation. And apparently, the training kept running. 7. The accidental experiment. When the researcher returned, the neural network had continued training far beyond the point where it had memorized the training data. And suddenly, its performance on the unseen test data began improving. The network had apparently discovered something deeper. It wasn't simply remembering. 22 plus 28 is equal to 50. It had learned a general mathematical structure. And it could use that structure to solve examples it had never seen before. The researchers called this phenomenon grokking. The word comes from science fiction writer Robert Heinlein. It means something deeper than simply knowing information. It means understanding it so thoroughly that it becomes internalized. And the behavior was fascinating. The network appeared to go through a kind of transition. First, memorization. Then, after much more training, generalization. It was as if the network suddenly reorganized the information it had learned. 8. The secret was in the representation. Researchers then tried to visualize what the neural network had learned. And they found something beautiful. The network had apparently represented the numbers in a circular structure. Imagine the numbers. 0, 1, 2, 3. All the way to 96. Arranged around a circle. To add two numbers, the network could effectively move around that circle. Start at one number. Move forward by the amount represented by the second number. And wherever you land. That's the answer. The network had discovered a structure that represented modulo arithmetic. It wasn't simply storing a giant lookup table. It had found a compact way of representing the underlying rule. And that is what made grokking so fascinating. The network had apparently moved from I remember the answers. 2. I understand the pattern that generates the answers. 9. But does it really understand? And now we reach the much bigger question. What does this tell us about artificial intelligence? Consider a modern large language model. You ask it a mathematics question. It produces a step-by-step solution. It looks like reasoning. But what is actually happening? Is the AI genuinely reasoning? Or is it producing an extremely sophisticated sequence of predictions based on patterns learned from enormous quantities of text? This question becomes particularly interesting when we look at systems like Google's Minerva. Minerva was built from a very large language model and further trained on scientific and mathematical material. It wasn't explicitly programmed with a set of mathematical reasoning rules, yet it could solve many mathematical problems. Give it a problem involving the equation of a line, for example. It can identify the slope, use the point given, construct the equation, and calculate the answer. From the outside, it looks like reasoning. But whether that represents genuine reasoning or extraordinarily powerful pattern recognition is still debated. And that's the uncomfortable part. The experiments give us evidence, but the theory hasn't caught up. 10. The strange land ahead. This is the central mystery of modern deep learning. We know these systems work. We can measure their performance. We can watch them learn. We can increase their size. We can train them on more data. And sometimes they suddenly develop capabilities that weren't obvious from the way we expected them to behave. But we don't yet have a complete theory explaining all of it. Why does an enormous, overparameterized model generalize? Why can some models memorize noise and still perform well? Why does grokking happen? Why does a neural network sometimes suddenly reorganize what it has learned? Why do certain representations emerge? And most importantly, when a neural network produces an answer that looks like reasoning, what exactly happened inside it? We don't have complete answers. And perhaps that's the most exciting part. Because artificial intelligence research may be entering territory where our machines are advancing faster than our understanding of them. A territory that researchers have described as terra incognita, unknown land. For decades, we believed we understood the basic rules of learning. Make the model too simple, and it won't learn enough. Make it too complicated, and it will memorize everything. Find the middle ground, the Goldilocks zone. But deep neural networks came along and started breaking the rules. They became enormous. They memorized. They generalized. They learned patterns we didn't explicitly teach them. And sometimes, after memorizing the answers, they appeared to discover the rules behind them. That phenomenon has a name: grokking. And perhaps the most important discovery isn't that neural networks can do this. It's that their behavior is revealing something about intelligence and learning that we don't fully understand yet. We built machines to learn. Now, they may be teaching us how little we actually know about learning itself.